Have you ever seen an AI agent in real life before? No? Well, I just happen to have one right here. Want to see how it's made? Let's jump right in. Oh, and it also lights up. You'll see. Before I walk you through the build process, let me give you a quick overview first. And just a quick heads up, this project is related to the animated n8n logo, which has quite a few similarities. Hence, I will skip a few parts that I covered in the other video. If you haven't already, please make sure to watch that first. It's linked down below. So here you can see a typical n8n AI agent pulled into 3D with a trigger node, which is a webhook here, then the AI agent, an LLM, a memory, an HTTP tool, and a respond to webhook node at the end. Now let's dig a bit deeper into this by starting with the base, which contains the mainboard and also a capacitive touch button to operate the device. An aluminum rod connects the upper body. It also acts as a cable channel to connect the mainboard to the LED connection board. On top of that, there are a few layers. Let me switch to the trigger node to explain them. The outer shell holds everything in place. Below the acrylic glasses, which also contain the icon, there is a diffusion layer, followed by a light guide, which sits right on top of an LED board. Since the light of each individual LED naturally spreads at a certain angle, it interferes with the neighboring LEDs. The light guide allows to have specific shapes projected onto the opaque acrylic glass independently, while preserving sharp boundaries between them. However, those separations also create shadows. And that's where the diffusion layer comes in. It adds enough distance so the borders get fuzzy, but the separation still looks clear enough. This combination was particularly difficult to design since there is just a tiny sweet spot where this works. The most difficult part might have been turning a square into a circle, which is necessary for the orange loading animation. The inner and outer shell of each node are held together with tiny pins, so everything can be disassembled anytime. To connect the nodes with each other, there are small cable channels designed right into the connecting edges. They are chamfered at the top, so they can be printed in place. The LED connection board sits right in the middle and allows for an efficient wiring. Just for reference, the first prototype has been soldered manually. It was a complete mess and absolutely time-consuming to assemble. The circular-shaped nodes have little notches at the top. This prevents the acrylic glasses, including the icons and also the light guides, from rotating freely. Now let's get into the build process. These are the printed parts, and there are plenty of them. They are made out of PLA NX2 from extruder. Components visible from the outside are silver. Inner parts are white, so they optimally reflect or pass through light. The diffusers are a bit brittle since the bottom layer is only made out of 0.2 mm of material. But that way it is relatively easy to produce a diffuser instead of having to use a special LED film manually glued to a frame. Now continuing with the assembly. The main body, which consists of the 6 nodes, is glued together to achieve the maximum stability. I'm using a more flexible glue here to fill in the gaps, but it fully hardens after 24 hours. Already here, the agent node gets the steering roll, the piece everything else attaches to. You can see that this part looks a bit different than the others. That's because I split it into 2 for easier manufacturability, so no support material is needed. I'm using the trick here of cutting the filament into small pieces to use them for proper alignment with the other part. Now I'm switching to CA glue since the 2 surfaces I want to glue together have no gap. And this also ensures to have a very strong bond of all components. After curing, I can then cut off the excess of the filament pieces so I have a flat surface for the LED boards later. Now I'm doing the same trick with the filament to attach the back mount to the back side. Also, this part gets glued together with CA glue for a strong bond. You may notice that the filament pieces I used were significantly longer this time and thus they stick out quite a lot. That's on purpose. They will later hold the LED connection board in place. Next, I need to prepare the aluminum rod. So first I use a tube cutter to cut it down to a length of 28.5 centimeters, which is just right so the nodes float in the air at a height that looks good to the eye. Followed by chamfering the edges, both from the outside and the inside. For drilling the mounting holes, I created this simple jig. It allows me to easily place the holes where they need to be. And with this mobile drill press, I can repeatedly create perpendicular boring results. Last step is to tap the holes, which I'm carefully doing by hand. Just need to make sure that I do it perpendicular. Now I can slide the rod into the base and fix it with 2 M4 screws. After that, the other end now can be mounted to the upper body. Same as with the base, the fit is very tight, so there can be no movement that could potentially wear out the screw holes in the aluminum rod. Now off to the electronics. First, I need to cut wires to length, which will connect the individual LED boards to the connection board. Again, I'm using the technique with a piece of tape to cut them efficiently to length. These wires have a solid core. This not only makes it easier to push them through the tunnels between the nodes, but this is actually necessary for being able to use the connectors soldered to the LED connection board, which I will show later in detail. Of course, the wires also have to be stripped. Next is soldering, starting with the square boards. First, I'm applying a bit of solder to the boards themselves. And then I place the ends of the wires into the molten solder. This is an 8x8 RGB LED matrix, by the way. It is an off-the-shelf component, relatively easy to source. Now off to the circular LED boards. Before soldering, let me show you first how they are designed. The schema itself is pretty simple. Power is wired in parallel, and the data line is wired in series. And every LED has a tiny capacitor right next to it to eliminate interferences. Drawing the traces was also relatively easy using circular rails, with the positive line on the front and the ground line along with the soldering pads on the backside. Here it is in 3D view. Now I solder the board the same way I did with the square boards. For comparison, let me show you how I did it with the first prototype with an off-the-shelf component. Since the rings were individually powered, I needed to do more complicated wiring, which was very time-consuming, but at least I didn't have to make a custom PCB that way. It enabled me to ship a new physical product within 3 weeks. Only on a larger scale though, it didn't make any sense at all. Also, with the custom board I could make sure that the exact same LED chips were mounted onto the PCBs, since I managed to get both from the same supplier. Before, I had to perform a tedious process to calibrate the colors of the LEDs. Now I'm finishing off this part by stripping the other ends of the wires. Same for the square boards. These are 3 components that I could reuse from the previous project, the animated n8n logo. Those are the LED connection cable, with the only difference that it's slightly longer, the mainboard, which controls the device, and the TTP223, the capacitive touch sensor, with the already soldered connection cable. Again, please make sure to check out the other video if you haven't already, so you get the full picture. There I am also sharing valuable insights about the lessons I learned, some material limitations, and a perspective on manufacturability as well as reliability. Now installing the LED connection cable, which is way easier in this project since there is plenty of space left inside the aluminum rod. Also here I'm stripping the wires. And since these are stranded wires, I also need to twist them a bit before soldering. Off to the LED connection board. It is fairly simple by design, but plays a significant role, enabling clean and efficient wiring. Every LED board has two power connections, an incoming data line and an outgoing data line, which connects to the next input again. In other words, I just implemented the routing so every LED board can be connected the same way. This PCB then makes sure that all LED boards are wired up in the right order. I was very glad to find these Phoenix connectors, which have a very low profile and are also specifically designed for the usage of LEDs. You probably know this procedure already, but let's quickly walk through it again. So to solder the custom boards, I first place a few boards of the same size around it, so I can fix the middle board well on the table. After that, I place the soldering stencil on top of it and fix it with a piece of tape. Then I apply some solder paste, and with a steel spatula I squeeze the solder paste through the holes of the stencil. And after that I can place the small connectors onto the liquid solder paste. And finally, using a hot plate, I can perform the soldering itself, and later on pull the boards quickly off of the plate so the solder can solidify. Now comes the assembly. First I add a bit of solder to the ends of the wires. And then I also add a bit of solder to the pads on the board. Then I need to make sure that I guide the wires through the cutout before I solder the wires directly to the board. Before mounting the LED boards, I need to add a bit of double-sided tape to the back of them so they stay in place properly, at least during assembly. I don't go all the way around though, to make the boards easier to disassemble if needed. The circular boards are a bit different. With this simple jig, I can easily place a piece of sticky rubber at a certain position of the board, which stops it from rotating since it interlocks with the cutout in the printed part. Actually, this is an old relic from the first gen circular board that I showed earlier. There, the wiring itself stopped the PCB from rotating. Now it's finally time to assemble the boards. For that, I push the wires through the tunnels and temporarily bend them upwards. This allows me to place in the board. And now you can also see why those pieces of filament needed to be a bit longer. They fit exactly into the mounting holes of the PCB. Now I can easily connect all the wires to the board without having to solder anything. Finishing with the two middle LED boards, which then cover up the insides of the agent node. Now let's jump to the base. There I can now insert the capacitive touch sensor and fix it with 2 drops of hot glue. Next up, installing the mainboard. Starting with the Wi-Fi antenna, which has plenty of room in this housing. And then I can connect both the capacitive touch sensor and the LED connection cable before I mount the board with 4 screws. Now it's time for the firmware. For that, I just plug in the device into my computer and load the firmware onto it using the Arduino IDE. Compared to the animated n8n logo, this firmware is way more complex. There are different modes, and the sheer amount of LEDs and the individual animations just create a lot of lines of code. I don't want to bore you with the details, but have a look at it yourself if you want. The code is open source, linked down below. Now let me do a quick test run first, just to verify that everything is working properly. Alright, looks good. So now I can peel off the protective layer of the double-sided tape and put the boards finally into place. Now comes the optical step. First, let me show you how this originated. I used a laser-cut opaque acrylic glass and applied a printed transparent sticker on it. Turns out it's a very tedious process since it requires some soapy water and a squeegee to have a picture-perfect finish, and it also takes a long time to apply. The other problem is that when I place another thin piece of transparent acrylic glass on top for a glossy finish, these weird artifacts show up randomly, caused by the printed layer, which tends to partially stick to the acrylic glass over time. So I had to come up with a different solution. I then found a manufacturer who printed acrylic glasses from the back and then finished them off with a white PETG coating, which at first glance was quite promising, but the quality was not good enough. Just look at the centering of the icons. And these here are just terrible. So also not an option. But then I came up with the idea to use non-sticky printed films, like the stickers from before, but non-sticky. Only downside, I have to manufacture them by myself because apparently there is no market for plotting non-sticky films. At least I could get the films printed in larger quantity. With that, I can now place them one by one onto a cutting mat, and then a plotter does the rest. After that, I can just peel off the remaining film and then peel off the individual pieces one by one with the help of a scalpel. In case you're wondering what those tiny square pieces at the top are, they just help with aligning the objects on the cutting area while preserving their real dimensions, since the plotting software has no built-in functionality for that. Now it's time to assemble the optical stacks within the outer shells. First, I need to peel off the protective films of the opaque acrylic glass. After carefully cleaning the printed film, I can place it on top. Then also peeling off the protective films of the thin transparent acrylic glass, which is placed next. And all these pieces I then place into the outer shell. Now I repeat this process for each of the other nodes. Here you can see the notches I explained earlier, which prevent the glasses from rotating within the housing. And these little marks help to distinguish the three similar looking but not identical parts. Next, I can place in the diffusers. After that, I can place the light guides onto the LED boards. And finally, mount the outer shells onto the main body. Now it's time to put in the final screws. The base cover has a tiny cutout, which aligns with the tactile switch of the main board, that can be accessed from the bottom with a paperclip or similar. One last detail, a silicone cap, to cover the USB-C connectors so users are not tempted to power the device via the USB-C port, which is not rated for this application. Alrighty then, it was a bit difficult to get it on camera, but off to the demo. Wait, we're not done yet. Soon after, n8n released version 2, which comes with a few design changes. So let's take care of that. Thankfully, it's not too much of a hassle, and more importantly, this device is built in a way that it's repairable for the most part. The agent and memory logos have changed, so I needed to get new films printed and had to plot them afterwards. And also, the animation has changed significantly. It's quite different, but I'll let you be the judge. Roll the demo. The animated AI agent comes with a USB to DC cable for powering the device. And this awesome user manual, which the n8n team helped bring to life, right down to their branding. With this, let's wrap up for today. I hope you enjoyed it. Don't forget to subscribe and see you next time.